Hello guys, and today we'll be talking about elimination of arbitrary constants. So we have elimination of arbitrary constants. So this is a differential equation topic. It's actually one of the first few topics of differential equations. We'll be trying to understand um, how the general solutions of differential equations uh, form a differential equation. So basically, it's just the reverse part of solving a differential equations. No, so it's better to for us to understand that first before we proceed to solving differential equations. Basically, so just take note of arbitrary constants first. What are arbitrary constants? These are non-numerical symbols, which is not a variable in a generalized operation, which means these are not the variables itself, but the values can vary. These are arbitrary. So we can actually assume any value of these constants. Okay. So general solutions, differential equations have arbitrary constants. They will always have arbitrary constants. And with the number or arbitrary constants, now the number of arbitrary constants will dictate the order of the differential equation. Okay. So now in eliminating arbitrary constants, once that we already know the number of arbitrary constants, we can actually already know the order of the differential equation. So just take note that the number of arbitrary constants is equal to the order of the differential equation. Okay. In short, when it comes to elimination of arbitrary constants, we need to differentiate the number of times equivalent to the number of arbitrary constants. So when eliminating arbitrary constants, step one, of course, is to count the number of arbitrary constants first. Okay, count the arbitrary constants. How many are they? So that we'll know how many times will be differentiate. Step two is to perform differentiation. Okay, it's differentiation, not derivation. We differentiate, we don't derive. So differentiation, so if we have four arbitrary constants, then we will differentiate four times. Then number three is to use algebraic techniques to manipulate the equations so that it results to a differential equation, of course, without the arbitrary constants. So these are the steps that we need to consider so that we can determine the differential equation. Okay, so let's have some examples here. Now, for the first example, let's try to find the differential equation of the family of curves, which are actually lines, that has a slope 2 and its y-intercept assumed as the arbitrary constant. Now, we're already given a value of the slope, and we have a hint. No, we are given a hint that is the y-intercept. So, what equation should we use for us to determine the differential equation? If we are given a line with its slope and its y-intercept, of course, we'll be using the slope-intercept form, which is y is equal to mx plus b. That's the slope-intercept form, right? So since the slope is 2, our general solution is 2x plus b. Y equals to x plus b. So b here is the arbitrary constant. Now, how do we know the order of the differential equation? You just have to count. So let's count the arbitrary constant. That's 1. So that's the only arbitrary constant in the equation. So we'll just differentiate once. By differentiating once, this is dy over dx. Differentiate 2x by the power rule, that's 2. The derivative of 0, the derivative of b is 0. So therefore, our differential equation is dy over dx equals 2. That's already our differential equation. Now, the elimination of arbitrary constant does not end like the first example easily. So how about this example? Let's try to differentiate, or let's try to determine the differential equation. So we only have one arbitrary constant here. So we just have to differentiate once. Differentiating it once, we have dy over dx equal to c. Then the derivative of sine x is cosine of x. Now, we cannot differentiate further. So how do we eliminate the arbitrary constant in this equation? There are few ways to solve this. It's either by substitution or simple elimination. So you just have to pick one method and you're good to go. So for us to eliminate the arbitrary constant, here's what I will do. I'll solve for c in the first equation, then I'll substitute it into the second equation. So from the first equation, let's write it here. To solve for c, we just have to divide both sides by sine of x. This gives us y over sine x. Then substitute into the second equation, we have dy over dx equal to y over sine x times cosine of x. But what is cosine x over sine x? Cosine x over sine x is actually a trigonometric identity. Just have to look into quotient identities. Okay? So cosine x over sine x is cotangent x. Therefore, the differential equation is dy over dx equal to y cotangent x. Now, let's take a look into a more common example of elimination of arbitrary constants. And a little bit complicated, not too complicated. Let's have this general solution. We have c sub 1 e raised to 2x, c sub 2 e raised to negative 3x. So as you may notice, we have two arbitrary constants, c1 and c2. Now, how do we determine the differential equation? So there are um, two observed ways or two developed methods in solving this. One is by differentiating right away, or and then manipulating, which is the more common one, the more conventional one. And two is more like forcing to be the arbitrary constant to be eliminated. Let's look at the two methods. First method, by differentiating right away. Okay, I'll write that as method 1, right? The conventional way. So let's differentiate the equation twice because we have two arbitrary constants. So that's y prime equal to, by chain rule, we have 2c1 e raised to 2x minus 3c2 e raised to negative 3x. Then differentiate it again. So this will be the second derivative. Now, by differentiation, we have 4c1 e raised to 2x plus 9c2 e raised to negative 3x. So we already have three equations here. Then let's try to eliminate the two arbitrary constants. But in this method, it's a bit hard or non-intuitive. Why? Because you have to notice some parts here. You really have to notice, and it doesn't have a more of a direct method of solving this, unlike the next method. So notice from the two equations, for c sub 1 e raised to 2x, when you multiply when you multiply this first equation, y prime, by 2, you get 4 c sub 1, right? So with that, we can actually eliminate c sub 1 e raised to 2x. Okay, so how do we do that? Let's call this equation 1 and equation 2. So let's try equation 1 times 2, right? Minus equation 2. What will be the result? So multiply the whole equation by 2, that's 2y prime, minus the second equation, this is 2y prime minus y double prime. Next, this is 4, right? This will be 4. 4 minus 4, cancel. Negative 6, that's negative, that will be negative 6. Minus 9 is negative 15, right? So here, we can actually solve for c sub 2. E raised to negative 3x, that's 2y prime minus y double prime over negative 15. Okay, next. How do we eliminate c sub 2 and solve for c sub 1? Okay, again, by noticing, when you multiply the first equation by 3 and you add the second equation, c sub 2 will be eliminated. This is negative 9 plus 9. So let's do that. First equation times the 3 plus the second equation. So we have 3y prime plus y double prime equal to, this is 6 plus 4 is 10, 10c1 e raised to 2x. And then this is negative 9 plus 9, that's 0. So solving for c sub 1 e raised to 2x, this is equal to 3y prime plus y double prime over 10. Right, now, we already have these two values. We can actually substitute that into the first equation for us to determine the differential equation. So we have y equal to c sub 1 e raised to 2x, that's 3y prime plus y double prime over 10, plus this one, that's 2y prime minus y double prime over negative 15. Okay, now let's try to multiply the whole equation by its least common denominator, and that's 30. Okay, so we have 30y equal to, that's 30 divided by 10, 3, 3y prime plus y double prime. Then that's negative 2 times 2y prime minus y double prime. So simplifying further, we can already solve for that differential equation. It's 9y prime plus 3y double prime minus 4y prime plus 2y double prime. Okay, simplifying further by adding like terms, that's 5y double prime. This is 5y double prime, sorry, 5y prime equal to 30y. Okay, transpose to the left side, 5y double prime plus 5y prime minus 30y. And of course, there's an obvious common factor there, which is 5. So therefore, the final answer is y double prime plus y prime minus 6y equal to 0. And that is the answer to this question. That is the differential equation wherein the general solution is this bit. Let's try method 2. Now for an alternative method here, as I have said earlier, you just have to forcefully eliminate every single arbitrary constant. This is a more direct way of determining the differential equation. But how? Okay. If we go back to the very first example, which is this, if you notice from the equation, if we have an isolated arbitrary constant without any other multipliers with variables, we can differentiate this and it ends up with 0, right? When it ends with 0, then that's the point where you can conclude that the arbitrary constant is eliminated. So we can do that here. How? How do we isolate C sub 1? Let's remove e raised to 2x from the equation. So how? Let's multiply e raised to negative 2x to both sides. Okay. Of course, let's distribute and take note, we'll use the loss of exponent in this bit. So we have e raised to negative 2xy equal to C1, that's e raised to 0, so that's C1 only, plus C sub 2 e raised to negative 3x minus 2x is negative 5x. There. C sub 1 is isolated. We can now differentiate. Okay. So differentiate. How do we differentiate this term? We have two expressions that are multiplied. This is a product of two expressions, y and e raised to negative 2x. So when you differentiate, you should use the product rule. When you use the product rule, that's duv equal to vdu plus udv. So when you differentiate this results to, okay, let's copy first e raised to negative 2x and then differentiate y, right? Then plus, okay, plus copy y, then differentiate e raised to negative 2x. That's negative 2e raised to negative 2x. Okay, a lot of students are uh, confused with that part, especially if they are not, the concept of product rule is not explained. Okay, next, for the right-hand side, this is a simple product rule again. So, sorry, simple differentiation. That's 0 already. This is negative 5c2 e raised to negative 5x. All right. Now, how do we eliminate c sub 2? Of course, by doing the same process as the first step, we multiply both sides by e raised to 5x. Why do we multiply e raised to 5x? So that 5x minus 5x is 0. So that the multiplier to c sub 2 is eliminated. Okay? And of course, use distribution, right? Product, you distribute. Okay? So multiplying this leads us to e raised to 3x y prime. Multiplying this leads us to negative 2 e raised to 3x y equal to negative 5 c sub 2. Okay. Now, from here, as you may notice, if we differentiate again, the second arbitrary constant will be eliminated already. So, differentiate. Okay, take note, we have two terms wherein we need to use the product rule. Two terms wherein we'll be using the product rule. So, for the first term, okay, copy e raised to 3x y double prime plus copy y prime, differentiate e raised to 3x. Okay, first part. I'll, I'll group it like this so that you can notice. Next, copy y, copy this, then differentiate y. That's minus 2e raised to 3x y prime. And then copy y, differentiate this term. So that's negative 6 e raised to 3x y equal to 0. Okay, then we are almost done. We just have to simplify the equation. Of course, this term is a common term, e raised to 3x. And at the same time, we cannot assume that e raised to 3x is 0, right? E raised to 3x can never be 0. It's always greater than or equal to, it's always greater than 0. to any value of x. So we can actually eliminate e raised to 3x right away. So this results to y double prime plus 3y prime minus 2y prime minus 6y. And there you go. The answer is y double prime plus y prime minus 6y equal to 0. As you may notice, we have the same answer. We have the same answer as the first method. Okay, let's take a look at this example. Now, going forward, with these last two examples that we'll be dealing with, let's try to use the second method that I have discussed, wherein we will forcefully eliminate every arbitrary constant. So let's have this general solution. This time, it is not exponential. Okay, it's not exponential. So, and then as you may notice, we have two arbitrary constants also. So we'll be differentiating twice. But as you may notice with the second method, let's go back a little bit. Here, yeah, we differentiated twice without even noticing, right? We didn't notice that oh, we have already differentiated twice because we are just focused on basically eliminating each constant one by one, one after the other, right? One after the other. Same is true with the succeeding examples. Let's try this. So maybe I want to eliminate C sub 2 first, just for the content. So for us to eliminate C sub 2 first, we need to multiply the whole equation by x cubed. So x cubed times y equal to C1x squared C2 x raised to negative 3. So when you distribute x cubed, it becomes x cubed y equal to C1 x to the fifth plus C sub 2. All right, then let's differentiate. Take note, we'll use the product rule here. Okay, so with the product rule, we have x cubed y prime plus 3x squared y. This is equal to 5c1 x to the fourth. One down. Another arbitrary constant. How do we get rid of c sub 1? We multiply both sides by x raised to negative 4 so that this will cancel. So, but of course, you still have to distribute. Okay? So this becomes x raised to negative 1 y prime plus 3x raised to negative 2 y equal to 5c1. Only then we differentiate for the second time. Right? Now, we'll be using the product rule twice again. So for the first term, the derivative is x raised to negative 1 y double prime. Then we have minus x raised to negative 2 y prime. Then for the next term, we have 3x raised to negative 2y prime minus 6x raised to negative 2y equal to 0. Okay? Slight correction. Wait, this should be raised to negative 3. There. Now, how do we simplify the whole equation? Of course, we don't want negative exponents in our equation. We never wanted negative exponents. So let's try multiplying the whole equation in a way that the resulting equation would be of lowest degree and would be of positive exponents. Let's multiply x cubed, right? Let's multiply x cubed. So this becomes, the first term becomes x squared y double prime. Then we have xy prime plus 3xy prime minus 6y equal to 0. And of course, by adding like terms, the final answer would be x squared y double prime plus 2xy prime minus 6y equal to 0. And that's how we determine the differential equation for this example. Now let's have the last example. This time, you're asked to solve for the differential equation of the family of curves, or in this case, circles, whose center is along the x-axis and are tangent to the y-axis. Right. So let's try to sketch a few parts of, or a few circles. Let's try to sketch a few circles here. Of course, we have a strict condition wherein the center is always at the x-axis. Well, let's call that center H0, right? That will be the coordinates of the center circle. But this is not the correct drawing because the condition is it should always be tangent to the y-axis. So let's translate a little bit this one. So this is the correct figure for the a certain circle amongst the family of circles. So we actually have an uh, infinite collection of these circles. We can actually draw here, we can draw here, here, we can draw on the other side, and so on and so forth, right? But we just have to consider one. Now, if we have a circle that is tangent to the y-axis, where in the center is along the x-axis, we can actually conclude other geometric properties. Of course, if we have a circle, we need a center and we need a radius. Of course, we need a radius. It's a circle. But we cannot we cannot conclude that the radius is also an arbitrary constant. Why? As you may notice from the figure, this is a radius. And this radius can be expressed in terms of the x-coordinate of the center because this distance right here is equal to the x-coordinate of the center, which is h. So the equation of the circle here that we will be dealing with has only one arbitrary constant, which is the letter h, or the constant h, right? Recall from analytic geometry that the equation of a circle with the center and the radius given is x minus h squared y minus k squared equal to r squared, right? Let's substitute. So we have here x minus h squared. Then if we have 0 as the y coordinate of the center, then that's simply y squared equal to the square of the radius, which is h. That's h squared. All right. Now, uh, forward thinking, if we differentiate this becomes 2 times x minus h. This will be another expression, and this will be 0, right? As you may notice, we have not eliminated the arbitrary constant at that point, right? We cannot simply solve for x minus h on the next step and then substitute it here because we have a squared term. It will be a little bit, a little bit, it will be, it leads us to a more difficult process. So what can we do is simply to simplify this. Let's expand this term and see what happens. So if we expand this using the binomial theorem, or just a square of a binomial, we have x squared minus 2xh plus h squared plus y squared equal to h squared. So I have said this will be simpler because the term h squared is eliminated. Now let's transpose 2xh to the right side. So this becomes x squared plus y squared equal to 2xh. Then let's try to solve for h by dividing both sides by 2x. We can already solve for h, and that's how we did in the first few examples with the second method, wherein we are to forcefully eliminate an arbitrary constant by isolating the arbitrary constant itself. So we have x squared plus y squared over 2x. We have already an isolated arbitrary constant, so we can differentiate it. So by differentiating this, of course, the left-hand side becomes 0. And how do we differentiate this expression? It is already a quotient, so we'll use the quotient rule. From quotient rule, we have v du minus u dv over v squared, right? Okay, so here we have the derivative of the numerator. That's 2x plus 2y, but don't forget the y prime. Then copy 2x. Then minus, copy x squared plus y squared. Then differentiate 2x. That's 2. And then the denominator is simply the square of 2x. Okay, but actually it won't matter this time. The denominator won't matter. Why? You can simply multiply that to the left-hand side. The denominator is eliminated. So we have 0 equal to 2x plus 2y y prime times 2x minus 2 times x squared plus y squared. Now, as you may notice, we have a common term, which is 2. So by dividing both sides by 2, we have 2x plus 2y y prime minus the quantity x squared plus, sorry, we have here an x, then minus the quantity x squared plus y squared. Okay, then of course let's distribute x. We have 2x squared plus 2xy y prime. Then distribute the negative sign. We have minus x squared minus y squared. Okay, and then simplifying like terms, x squared plus 2xy y prime minus y squared. Sometimes I don't want the 0 on the left side, so I'll just flip the equation in this manner. And this will be our differential equation. Okay, so what have we learned in this discussion? So first, differential equations have general solutions, and the general solutions usually have what we call arbitrary constants. Just like this, arbitrary constant, right? So arbitrary constants are these constants wherein we don't know the value, but it can be any value. And the number of arbitrary constants in a general solution corresponds to the order of the differential equation. And we have learned two methods of finding the differential equation for a given general solution. One is by differentiating right away after we've already known the number of arbitrary constants, and the other is by forcing every arbitrary constant to be eliminated until we don't have any arbitrary constants in the equation. And we, of course, solved some examples, including some word problems. And that's it for today. Thank you for listening.